Okay, so we would continue our discussion on the center of mass a little bit more. The concept that we introduced in the last lesson. Okay, so one of the things that you were not getting probably, I just want to clarify a bit, and this is a continuation of the last lecture, that when you throw a chalk, an object like this, whose center of mass is tracing a parabolic trajectory, and all other points are not. And I said that all other points are not because of the internal forces, right? Now when I throw this chalk, the center of mass, of course, maintains the parabolic trajectory. Every other point would like to go in a straight line, right? Would like to go in a straight line, but because now there is a rotation, because the way I threw it up, so if the chalk's position is like this, okay, so now this point only experiences the force of gravity and traces a parabola, while every other point experiences both the external force and the internal forces. So ideally, if they were only seeing external force, then the chalk would trace a parabola. The whole of the chalk would trace a parabola. Otherwise, if they had some initial velocity, any of the objects, that is what I am doing. Each point, when I'm throwing, has some initial velocity. This point would like to go in a straight line, okay, relative to the trajectory. So what keeps it not going into the straight line? You have to provide a centripetal acceleration, right? And that centripetal acceleration is provided an internal force. Otherwise, the chalk would break apart. Okay? The internal force that keeps the other particles going around the center of mass when I'm throwing it like this is basically the internal forces providing the required centripetal acceleration to keep all other points going around it. That's how internal forces play a role.
So let's say, for example, this is a javelin. When we throw a javelin, it follows all points follow the parabola. वो सिर्फ इसलिए कि all of the points are thrown in the same direction or velocity भी उनकी they're all acting in the same direction. मतलब जो like a javelin, right?
Yes.
When we throw a javelin, so all the points seem to follow the parabola.
Yes, because of course that the two things determine it's the initial conditions, okay, and then the external forces, okay. So we'll talk about that in a minute, okay.
Sir,
Yes.
basically what you're saying is the internal forces are what cause the other particles to stay around the center of mass. Otherwise,
Yes.
they break apart. That's it.
Yes. Otherwise, they have some initial velocity, right, and then the gravitational force, right. So they would have their own trajectory, right. The way they are being constrained and move in complicated fashion around that point is because internal forces are providing the centripetal acceleration to keep them around. Otherwise, they would just break apart.
Initially, velocity comes
When I'm throwing it. Okay, and the second bit that I wanted to talk about this was why center of mass motion is still good. Now imagine a cricket ball, all right? Where is its center of mass? It's a sphere in the center, okay? Now if I could track the center of mass motion of a cricket ball, at any point I can calculate where the rest of the object would be because its radius is fixed, it's not deforming. So you see the center of mass description is very good for many objects. The same holds for a football. So sometimes it's just the shape of the object, the center of mass motion is good enough, and when you know the final position of the object of the center of mass, then you see you can trace the boundary around because it has a fixed shape, right? Symmetric fixed shape. The rotations do not matter, right? However it rotated during the trajectory. The third example is that sometimes the details are not really important. I give you a very drastic example. When you are throwing a missile on a target, okay, a building of this big size, let's say, and the size of the missile is probably a few meters long and a few feet wide, right? You don't really need to know how, in which direction it hits the trajectory, in which orientation. All you need to know is that its center of mass, the center of mass's final position is somehow in the building, right? So sometimes the detail is not important. Other times the shape of the object is such that we don't really need to describe all the motion, okay? That does not mean that the description of the rest of the particle's motion is not important. We would discuss it to some length in the next section when we do rotational motion, okay? But this is the justification why center of mass is still a very good approximation, a good assumption to work with examples, physical examples, okay? And then now, since we have already established the center of mass is a very good description, it also means that for complex objects, for like an object like a triangle or pyramids of Egypt, okay, or any other irregular object or semi-regular object, not where the center of mass is not obvious. Center of mass of a sphere is obvious, right? But the center of mass of a triangle may not, okay? In such cases, to apply the center of mass description, we need to find the center of mass. So in the next few minutes, we are doing a few exercises how to find the center of mass of an object. All right? So the center of mass, the most general definition that we obtained last lecture was this. For an n particle system, all right. Now you see this is a vector equation, right? It means I can write left side as xex plus y ey. So this is capital X is the x coordinate of the center of mass, y is the y coordinate of the center of mass, and z is the z coordinate of the center of mass. On the right hand side, I can write m sum 1 to n mi xi ex, the x coordinate of the ith particle, okay, the y coordinate of the ith particle, you see this? Now since this is a vector equation, I can just compare the components, right? X component on this side would be equal to the x component on that side, y component equal to y component, and z component equal to z component. So basically I can write 3 scalar equations, if you like, a much simpler equations that you can, and this is very useful practically, then instead of solving a vector equation where sometimes the sum becomes integration and then it becomes quite difficult to deal with integration of a vector, right? So you can just split this into 3 scalar equations for x, y, and z, and then you solve it. And once you have found x, y, and z components, you basically have found the center of mass. So x then becomes 1 over m all right. Similarly, see,
x तो वेरिएबल ही होगा.
हाँ, yes, वेरिएबल है. x I भी वेरिएबल है, x भी वेरिएबल है.
हम सारों के x कोऑर्डिनेट्स को फिर ऐड करेंगे.
बिल्कुल, all particles के x coordinates को ऐड करेंगे, then you would multiply for each particle's position in x direction, x coordinate with its own mass, and then you sum it. You get the vector equation if you add all these three equations together, right? Okay, so now having said that, let's apply this and also generalize the center of mass sum a little bit more, okay? So let's say that we want to calculate the center of mass of a rod of length L whose mass is m. Okay, and now and it has it has non-zero length, its width and thickness are 0. Okay, and now how many points do we have in this object? Infinite points. So this summation really is not the most practical way to calculate. It's best if we treat this object as a continuous object and try to do the integration instead. And how to do that? Let's see. So to do that, let me just make a coordinate system, okay? This is y-axis and this is x-axis, all right? Since I said that it's a rod of length L and its dimension in z and y are 0, its thickness and height are 0. So that already gives me that z and y are 0. Okay. Now we only have to calculate x. Okay. Now this is if we knew somehow each particle in this system, its position and mass, we could just add, but this sum really is infinite sum, right? So let's do that. Let's apply the infinite limit, right? So then limit n goes to infinity, okay? But before that, let me make a little bit more interesting. This object for our purposes really is continuous, okay? Now we take a small width, we chop this into small pieces of width delta x, okay? All right? That is the width of the object, and we say that there is a mass dm in that width. That little piece of the rod whose width is dx has mass dm, and its position from the center from the coordinate system is x. So once we know that, can I apply this formula here, and let's say that we have such n segments, n such segments. So can I write then one to n mi, we have dm, right? Mass of each segment. I can put an I here if you like, and then the position of the segment, right? That is the definition, mass times its position, right? And now we make this segment infinitely small, which means the number of segments go to infinity, and we apply the limit. N goes to infinity, dmi xi. That is what? Integral. I think I missed a 1 over m here. Okay, so this becomes 1 over m integral x dm. Now this is a more general way of calculating the center of mass for a continuous object, okay? Yes?
Why don't we say dx too? Because x is also very small.
No, x is not small. X is the distance from the center. X is not small, it is the dm which is small, right? X is the position, right? Now, it's not very easy to do this evaluation because we have variable x and then which is integrated with respect to dm, right? Now, if we could find a way to express the dm in terms of x, then we would be able to do this integral, okay? So now we know that total mass of this object is what? M, and total length is n. So how much mass is sitting in 1 unit of length? M over L, M over L, just M over L. So this much mass belongs to 1 unit length of the rod. And how much mass is sitting in length dx multiplied with dx, right? So if you multiply it with, and if you like, this is linear density, mass per unit length, okay? So this really is dm, okay? And now we plug that back in and you see that we have been able to describe dm in terms of two constants, mass and length, and dx. So we rewrite this equation, 1 over m, and now I can also use the limits from 0 to L. X m over L dx. So you take m outside, m over L outside, m cancels, and you have 1 over L 0 to L x dx, okay? So what is that integral? X squared by 2, then you plug in the limits, that becomes L squared by 2. L squared 2 multiplied by 1 over L is L by 2. The result is not very surprising. Actually, you could have guessed already. If this was a rod of uniform mass, this is exactly, you would have just guessed it, right? It's not very remarkable, but it shows you how to apply this method to a bit more irregular shaped objects, okay? This is how you do it. There is another important point. This calculation, if you look carefully, would have been even simpler, and the answer would have been different if I had placed the rod evenly at the origin. Its middle point at the origin, what would be the center of mass x coordinate? 0. Why? Because these segments dmi xi on the left side would be negative sign, an equal number of these segments on the right hand side would be with the positive sign. All of them would add to give me 0. So this value, the absolute value, is not important. It really depends on the choice of the coordinate system, okay? And if you have symmetry in the object, and you choose the coordinate system carefully, then the calculation of the center of mass becomes a lot more easier. In some cases, you don't really need to do the calculation. For example, if you are asked to calculate the center of mass of a rod of symmetric distribution, like it's not uneven rod, it's a uniform rod, then you just, by symmetry, you know that the center of mass would be in the middle of the rod. Doesn't matter, it's not really, it has to be defined, center of mass has to be defined relative to the object itself. It's the center of the rod. Then it really depends whether you place the rod at the center of mass or not. But you're better off whenever you take an object and it has certain symmetries, try to choose the coordinate system in such a way that object around most of the axes, out of 2 axes, let's say, or 3 axes if it's a 3-dimensional, try to place it in such a way that it is symmetric in at least 1 or 2 dimensions. Then you are left with only doing the calculation in the 3rd dimension. You see what I mean? So the choice of coordinate system is important, although the final answer remains the same. Doesn't really depend. It's only the calculation which becomes easier. Okay, now let's do another example. Now we have an equilateral triangle. Okay, yes?
One question. When we're solving like questions, like do we need to know like the general center of mass for certain shapes, or can we just do it like without knowing anything?
Sorry?
When we're solving these questions, let's just say we're looking at a joint, like a joint shape. Do we have to know the do we have to know the general like center of masses of each individual shape, or can we just do it as if?
I don't know the answer to your question honestly because I don't understand. It really depends on the situation. Okay? So I am showing you a few examples and then you would know a few examples. What I can tell you is that sometimes you would have to calculate the center of mass of an isolated object or two objects put together. Okay? So now we have this equilateral triangle, a sheet, okay, whose thickness is 0. Okay? Thickness is 0 and it's a plain sheet. Now we have to calculate the center of mass of this. Okay? So we choose a coordinate system. X and Y. Okay? Now because its thickness is 0, so Z is going to be 0, right? But now look at the symmetry. Is there a symmetry? Any symmetry in this object? This object is symmetric around x-axis. So it means its center of mass, the y coordinate of the center of mass is never going to be lie anywhere else other than on x-axis because of the symmetry. So I don't really need to worry about y. So that is when you can exploit symmetry. Okay? So that means that y is also 0. Okay? So, but it's not symmetric along y-axis, which means the x coordinate is not guaranteed to be 0 or in the middle. So we really need to find the x coordinate because if you look at the object in this direction, it's not symmetric about y-axis. Okay? There is no line that I can draw which would divide it equally. Right? I can draw a line perpendicular to y-axis which divides it equally. So then I really have to do the calculation for the x coordinate of the system. And of course now in the integral form the general formula is what? 1 over m integral x dm. Again the same thing that we used here. And the only difficult bit is that you need to calculate, you need to find a way to express dm in terms of x so that the integral becomes manageable. We can actually practically solve it. And that is what we are going to do, okay? To try to express dm in terms of x. Now in order to do that, again, and this equation in the context of this object, what it means is that I have divided this object into strips, okay, of dx width, okay, and each strip has a mass dm, and the position of the strip from the origin is x. Okay? So now I'm only calculating the x coordinate of the center of mass of this strip, and that would be given by this formula. All right? So now if I could find this dm in terms of x, then I would be able to do the integration. And by integrating, I means I'm adding all the mass belonging to each of these strips multiplied by their positions, added together, that gives me the center of mass, divided by the total mass, of course. And to do that, first of all, I need to find out what is the value of y at the top of this strip. For each strip, the value of y is going to be different, right? Because each strip has different height along y. So the value of y in this case what is this value going to be? No. Sorry? देखो एक और चीज़ है. Look, this line, this is a straight line here that provides the relationship between x and y, right? We can find y in terms of x, right? The only thing we would not know is the slope. So I can write basically here y is equal to mx. Okay? So let's say that we know this angle theta, tan theta, then the slope would be y is equal to tangent theta times x. And tangent theta, sorry, one more thing that we know we are given is we are given the height of this triangle. This quantity h here we are given. Okay? We are also given the base of the triangle. This is w. Okay? And then this would be w by 2, right? Because it's symmetric. Now I can express tangent in terms of h and w2, no? Tangent would be w2 over h, tangent theta. So I can write y equals w2 over h times x. Okay? So now this is the height of this particular strip, and you change x, you would change y. If you go here, right, if you take this strip here, then its height would be, its top position of its top coordinate would be this one. Okay. Now what about the length of the strip? So this was the coordinate of the top position here. What would be the length of this strip in terms of y? 2y, right? Because from 0 to here is y, and the total would be 2y. So the length of the strip would be 2y. And what about the width of the strip? I'm using small w because I've already used capital W over here. So this is dx, right?
सर आप रिपीट कर सकते हैं तो आपने दो स्टेप किए हैं एल के लिए और स्मॉल डब्ल्यू के लिए.
देखो यहाँ से लेके यहाँ तक जो स्ट्रिप है ये y है, इसकी लेंथ, ठीक है? तो पूरी स्ट्रिप की लेंथ कितनी होगी? 2y. और इसकी विड्थ तो गिवन है हमें, dx है, हमने अज्यूम की हुई है. So we know the length and width of the strip, and once we know the length and width of the strip, that means we know the area dA. Let's say that area of this strip is dA, and that would be length times width of the strip, which is 2y dx. dA is equal to 2y dx. Yes?
So ये strip like trapezium type नहीं बनेगा या dx बहुत छोटा हो जाएगा?
बहुत छोटा है ना, ठीक है? Okay, so now you have dA equals 2y by dx, and we also know y already. So we can write the dA area in terms of x, okay? And dA now becomes 2 w over 2 over h x dx, all right? And this 2 cancels. So area of this strip is w over h times x dx. Okay? And now we focus on dm. What is the mass per unit area of this strip? Sorry, this triangle. What is the mass per unit area of the triangle? M over area of the triangle. And what is the area of the triangle? Sorry? Half base into height. Half base into height. So the area per unit sorry, mass per unit area is m over A, and the area of the triangle is half WH. All right. Now this is the area per unit mass per unit area. Okay. What would be the mass in area dA into dA? All I have to do is multiply it with so dm is mass over A into dA and this. So dm then becomes, now I have already calculated dA, right, down there. So I plug that dA in here in this relationship and I get m over half HW into W over H x dx. There is some simplification, this cancels, okay, and dm becomes 2m h squared x dx. So now we have been able to express dm in terms of two constants and x and dx. Yes? dm is equal to this one. देखिए ये पूरी ट्रायंगल है, इसका पूरा मैस आपको पता है, ठीक है, और पूरा एरिया भी पता है. मैस क्या है इसका, एरिया क्या है इसका, एरिया क्या है, what is in terms of the known quantities h and w? We know the base and height of a triangle, half base into height, right, 1 by 2 hw. So you know both of these things, right? What is the mass per unit area? How do you calculate mass per unit area? When you know the total mass and you know the total area, how do you calculate mass per unit area? You divide mass by area. That gives you mass per unit area. Okay? Now we want to calculate mass in 1 meter square. How would you calculate it? You just multiply 1 meter square with that, right? And that gives you the mass in 1 meter square. आगे बात समझ?
So ये capital L किसी पर ट्रायंगल उसकी स्ट्रिप की लेंथ है?
Yes, of that strip. Yes, length of the strip.
Vertical length.
Yes. Okay. And now the rest is just a formality. X is equal to 1 over m x, and then we plug in dm in that integral up there. So 2m over h squared x dx, and what would be the limits on x now? 0 to h. Shabash. All right, and this integrals, you take the constants out, m cancel, so you have 2m over m h squared 0h x squared dx, and if you simplify this, this becomes 2 by 3 h. Okay, so 2 by 3 h, and the way we have defined the coordinate system, this is h, and at 2 by 3 h you would have the center of mass. So what would be the distance from the base? 1 by 3 h. You see there is asymmetry in this direction, and you expect more mass towards the base. So that is where center of mass is located away from this and closer to the base, because distance from this side is 1 by 3 h. Now you also have to be careful that this value 2 by 3 h or 1 by 3 h, really the answer could be different if I had chosen the origin on this side. then the answer would have been 1 by 3h. And if I luckily chosen the origin to be at the center of mass, there is no way of knowing it, right? Before you do this calculation, then the center of mass would have been 0. Okay, so this makes sense? So this is how you are going to apply this concept, calculating the center of mass, and you should expect this being tested. Okay, and you see the important thing is that you start with this for each coordinate, and then you try to express dm in terms of x. Okay, and then the integration is relatively simple in most cases. There would be more examples in the recitation and assignment. Yes? Once I have been able to express the integral in terms of x, then you see that x, this object starts at 0 and its most extreme point is at h distance from the origin. So that is why the limit is 0 to h. Ji? That is what I am trying to find. I don't know that, and I have to include every particle, every mass, every bit of mass in that system. So I have to integrate over the whole object. Okay? Yes?
So यहाँ पे मतलब जैसे for example अगर हमारे like limits system यहाँ अगर लिमिट करते हैं minus L और L से वो 0 आ जाता है. यहाँ पे कौन सी लिमिट मतलब अगर हम अपना origin ही choose करते 1 by 3h तो फिर हमारी लिमिट्स चेंज रहती और उससे फिर वो खुद ही सॉल्व होके 0 आता है ना.
Yes, then your limits would have been minus 2 by 3 to minus 1 plus 1 by 3.
And I would have solved to 0 anyway.
Yes.
That's how they work.
Yes. Okay, so now we are going to learn something new. Linear momentum. Okay, you're familiar with the concept at least to some extent before, so we're going to take another look at it. Okay, and we are also going to reformulate Newton's second law a third way. What was the second way? Work energy theorem. So that was a reformulation of Newton's second law, right? And we did it because it's useful solving certain problems which are relatively difficult to solve directly applying the Newton's second law. Okay? But it also led us to a very important and fundamental law. What was that? The law of conservation of energy. Similarly, this is another reformulation of Newton's second law. Okay? And it would also lead to another conservation law. Okay? So let's see that.
सर सेंटर ऑफ मैस में एग्जाम में कंपाउंड शेप्स का भी आ सकता है
जी आ सकता है
और 3D
जी आ सकता है पैरामिड्स का आ सकता है तो फिर that's I think general enough, right? If you are asked to calculate the center of mass of a pyramid, that's 3D, right? So we go back to again our definition of the center of mass of a system of particles, and that we know is nothing but sum from 1 to n mi ri divided by m. Okay? Now I can take a time derivative on both sides, right? Is there any issue with it? No, right? Right? Now what is this? The velocity of what? The center of mass. Now this is constant, this is also constant, and sum is linear, right? And when I have just a summation, I can just take the derivative of each term, right? And in each term I have m and m, so which are constants. So I can really take the time derivative of each of these r terms, right? Each of the position vectors. So on this side I can write sum 1 to n mi over m, or maybe just divided by the whole thing. Sorry. What is this? Velocity of what? No, velocity of ith particle. Ith particle, right? One of the particles. And then I have a summation, so I have all the velocities on the right hand side. So I can write this as mi vi over m. Now you see, we were able to define the center of mass as mass weighted average of the positions of all particles. In a similar way, we are able to define the velocity of the center of mass as mass weighted average of the velocities of each particle. Right? So this is how the velocity of the center of mass is related to the velocities of all the particles in the system. Exactly like capital R, the position vector of the center of mass is related to the positions of all particles, mass weighted average in both cases. Fine? Yes?
सर तो अगर हम इनको साइड चले जाएं तो वो मोमेंटम ऑफ सेंटर ऑफ मास
उस पे आते हैं अभी एक मिनट. Okay, so now I write back the Newton's second law that we arrived at when we applied it to the Newton's second law to a system of particles, and we arrived at a Newton's second law for the center of mass of a system of particles, right, which is only affected by the external forces and is equal to mass of the system times the acceleration of the center of mass, right? This is what we did in the last lesson, didn't we? Right? And now I can write this right hand side as well like this. dV over dt. Is there any problem with that? Just used one derivative to get the velocity, another derivative is still there. Okay? And now since this is a constant, I can take it inside and outside it, right? So I rewrite the right hand side as d mv over dt. All right? Any problems with that? Remember, this v is capital V, the velocity of the center of mass, okay, of a system of particles. And I say that this quantity, I define it, it's a vector quantity, it's a scalar multiplied with the vector, is again a vector quantity. So I call this quantity P m times V. Then the Newton's law for a system of particles becomes Fe is equal to dP over dt. This is another way of defining Newton's second law, where the quantity P, a vector, is nothing but linear momentum, which is a vector mass times the velocity of the object, okay, and it is always in the same direction as the velocity of the object, as you can see. Okay? Now this, there are several reasons. First of all is, this is how Newton actually wrote his second law. not F is equal to ma. The only thing is that he did not call P a momentum, he called it a quantity of motion. Okay? But the original definition of Newton was this. The second thing is that this is more general. This is more general than F is equal to ma. Anybody knows why? Why is this definition of Newton's second law more general?
Mass can be variable.
Yes, mass can be variable. Very good. You see this now. Now let me deconstruct it. Okay? I said that this is more general. mv. For most systems that you deal with, mass is constant. But aren't there systems where mass is not constant? For example, a rocket. In that case, mass is not a constant. So then if you expand this derivative, so this becomes dm over dt v plus m dv over dt. Now F is equal to ma is a special case of this definition, because when mass is constant, this term goes to 0 and you get back F is equal to ma. But for a system where the mass is not constant, then you get this term, which you cannot get with simple definition of F is equal to ma, unless you use this definition. And this definition is the basis of rocket equation. Okay? We would learn about that. Yes? नहीं कर सकती, वो देख लेना. नहीं, अभी अगली उस पर बात करते हैं 1 मिनट में. ठीक है? नहीं कर सकती, क्योंकि देखो जो हमने ये डेरिवेशन की है सारी, ये वाली, ठीक है, वो उसमें देखें ना सिर्फ एक्सटर्नल फोर्स है. They cannot, well, we'll talk about that in a minute. Okay? So but you get this now, right? This is the most general definition of Newton's second law, and P is, as Newton called it, quantity of motion. Okay? Mass times the velocity. Okay? And time rate of change of momentum is equal to the force, or the force is equal to the time rate of change of momentum of an object. Okay? Now this makes more sense because it has both quantities. When you have a car moving at 5 meters per second coming towards you, and you have a football moving at 5 meters per second towards you, which one is easier to stop? Okay? What you really have to deal with is the momentum of the object, not just its velocity. Okay? And that is covered here. All right? And also, this is used, this principle is used designing the safety of automobiles. Because you see, your car is moving with a certain momentum, okay? And now the quantity of force really depends on how quickly you change that momentum. How quickly you change that momentum, and that would determine how fast you are tossed out of your seat. Right? So let's say that you're driving a car, God forbid, not in real life, which is made of infinitely rigid material. And then you hit another car of a big mass, or a truck, which is again made of an infinitely rigid material. And the moment you hit, immediately the force goes to maximum and the momentum goes to 0. That requires a huge force. That involves so you are tossed with an extreme speed, right, towards the front of the car. All right? And then the impact is going to, of course, hurt you, okay, and sometimes fatally. Okay? But then, now with the cars, the way they are designed, their bonnet is designed in such a material that it's not too hard and it's not too soft. Because if it is too soft, the car is going to crush and you're going to be killed by crushing. But if it is too hard, then the impact is going to be on impact, the force is going to be too large. So you want the momentum to come to 0 from whatever speed with taking a little bit of time, and that helps you decelerate more time. Okay? Now if you are wearing the seat belt, you would slow down with the car. But if you're not wearing the seat belt, you would be tossed. All right? So this principle is literally used designing the cars.
तो इस केस में अगर हम गाड़ी में जा रहे हैं वर्सेस हम ट्रक में जा रहे हैं तो ट्रक का मोमेंटम ज़्यादा होगा, स्पीड सेम होगी.
Yes. That's why if you're driving in an SUV, unfortunately, you're safer than driving in a smaller car.
SUV में उसका मैस ज़्यादा है तो मोमेंटम ज़्यादा ही होगा, आपका मोमेंटम ज़्यादा.
Yes, but then it would decelerate still less compared to the other objects. So we will see that. We'll see that. Yes.
The same thing when you punch a pillow and when you punch a wall, it's different. It hurts less with a pillow because it's.
Yes, because so that's good. If you punch a pillow, or if you punch a wall, the pillow hurts less because you again come to the rest, right? But over a more extended time, so the total force involved, the magnitude does not go high. Okay. If you look at the graph in a collision, if you look at the graph of a force, okay, this is how it looks like. On this side I have time, and on this side I have force. For a when you hit a wall or when two rigid objects hit each other, this is the curve looks like. The force goes a lot, the magnitude. Now if you are hitting a softer object like a pillow, the force would go something like this. And you see, the magnitude of the force is smaller and it's spread over. Okay, it's being applied for a longer time, but the total magnitude is lower. If you're hitting a very rigid object, okay, that is why this is used in the design of the cars, so that the metal that is used in the front or on the engine side is hard enough to protect you from crushing, but is soft enough that it spreads the force over time. Okay, and that is why you should wear seat belts. And when you have an infant in your car, less than 2 years, should be back facing in this car seat, right? Because the necks are not strong enough to sustain the impact if there is an accident. All right. And now, see this, I've already defined somewhere V, right? In this case, that is V, okay? If this is V, if I multiply it with this side, with total mass of the system, this becomes mv, the total momentum of the object or the momentum of the center of mass of the object as, okay? Sorry, this is the total momentum of the object, okay? On the right hand side, if I multiply with m, this m goes away, okay? And what is this MIVI? Is PI, momentum of the ith particle, and this m gets cancelled. So what I have here is MIVI. So this is nothing but the total momentum of an object is equal to the sum of the momenta of all the particles. So now this is the relationship. You see, this is the relationship between the center of mass position with the position of individual particles. This is the relationship of the center of mass velocity with the individual velocities, and this is the relationship with the total momentum of the object with the momentum of each particle. It's simplest of all three, just linear sum. Yes? But mass to puri hai na uski. That would be the total momentum of the object. Still, its total momentum, as you can see, is the sum of all the momenta. So this is total momentum. You can be convinced from this equation as well. Okay? So now we reuse this and before I move on, this reformulation is particularly useful for the examples that I just gave you. Whenever you're dealing with collisions, the force is time dependent. The force is, it changes time, and it changes in time, it changes very quickly, and more often than not, we do not know its analytical shape. Okay? In that case, if you have time dependent force on this side and ma on this side, let's say this definition of Newton's law. Now this force is time dependent. For collisions or such systems, it's very difficult to solve Newton's laws in this form. Okay? It's much more easier here. Okay? And I'll show you why and how. Okay? Because the external force is now time dependent. Okay? And it's difficult to integrate this equation. It's difficult to find antiderivatives, to find position as a function of time, or to find the dynamics of the object. Now let's say that we have a system of particles, and it's possible to design a system of particles in different contexts where the external force is 0, which means all external forces, there is no net external force acting on the object. All right? We are assuming a situation where there is no external force. If there is no external force, what does this mean? dp over dt is equal to 0, which means the total momentum is constant. That is the law of conservation of linear momentum. Okay? But remember, this is only true when the total external force on a system of particles is 0, then the momentum is conserved, then the momentum is constant. Okay? Now this is the second conservation law. Okay? And you would be surprised that the law of conservation of momentum is more general, is more fundamental than the Newton's second law itself. Because if an object is moving very fast, close to the speed of light, you cannot apply Newton's second law, it fails. Or if an object is too small, for example an electron, okay, again you cannot apply Newton's second law to it, it fails, right? You need a more fundamental different theory. In one case, high speeds, you need relativity, and in low dimensions you need quantum mechanics. So in both cases Newton's second law fails, right? Conservation of momentum is still true, is still valid in both of those situations. So in a way, this is more fundamental than, in fact, until today we have not found any example in the universe, any example at any scale where this was not true, where the law of conservation of momentum was violated. Its violation has not been observed. That's why we consider it very fundamental. Sorry?
Law of conservation of energy, or
Yes, law of conservation of energy is as fundamental as this one, yes. And now this law of conservation of momentum we are going to use a lot, particularly when we are dealing with collisions, okay? So let's do an application of the law of conservation, okay? Let's say that there is a boat, okay? Okay, of mass m. Okay, and you are standing. It's in a, let's say it's in a standing lake. The water is not flowing. Okay, and you're standing on one end of the boat. Your mass, let's say, is m. Okay. Now there are 3 external forces on this system. So my system now, be careful, water is not part of the system, only two objects are part of the system. This is very important. The internal forces can change depending on your definition of the system, right? So how you define the system? If you define the system as Earth-Moon system, then that interaction or the gravitational attraction between Moon and Earth is an internal force, but the gravitational pull due to Sun is an external force. But then if you define the whole solar system as your system, then all the gravitational interaction between planets of this solar system and the Sun become internal forces, and any forces that you are experiencing from other stars or galaxies would become external forces. So the definition of internal and external forces is really depends on the definition of the boundary of the system. So I define my system as containing one person and a boat. Okay. Now there are three forces. There are three forces being exerted on this system. 3 external forces. Can you tell me what are those 3 external forces? The gravity. Gravity and buoyancy, right? Buoyancy, the force of buoyancy, which keeps objects afloat. Okay. And then the third force would come into play if I start walking, right? If you start walking, then if I start walking on the boat, it means that I am exerting a backward force on the boat. Boat is exerting an equal opposite force on me, that's why I am moving forward, but boat would try to move backwards, and what would resist its motion in water? The drag force due to water. Okay. Now let's make this simple. Yes?
So how do we decide how do we have to define our system?
Now that's really subjective. Depends on problem to problem. There is no recipe for that. How do you define, how do you choose what is your system is really subjective. It changes from problem to problem, okay? So for this problem, I am saying that the drag force is 0. Like we set friction to 0 to create ideal conditions to make a point, right? To understand a model system. So I am saying that the drag force is 0. There are 2 other forces, the weight and the buoyancy. Now, because there is no acceleration, the boat is not moving vertically, water is standing, both of those forces are equal and opposite in magnitude. So they make a net 0 force in y direction as well. So what I want to say is that all external forces are 0, okay? And the total momentum of this system is going to be constant. That what constant? Sorry? Initial momentum कितना है? 0 है. Nobody is moving. So that constant, you can take it constant, but you can also easily set that constant to 0. So let's say the total momentum of the system is 0. All right. So it means that I can write the momentum of the person plus the momentum of the boat is equal to 0. All right. And now I start moving on the boat in this direction. Remember, there is no external force. There is no external force, and whatever force I am exerting on the boat or the boat is exerting on me, both of these are internal forces. And internal forces we don't care when it comes to the conservation of momentum, right? They do not play a role. Okay, let me make the point, please. So I am moving with velocity, and since all the motion is in one dimension, I'm just going to treat these quantities as scalars in y dimensions, right? So this is y component of the momentum of the person plus y component of the momentum of the boat is equal to 0. So what is my momentum in that case? M Vm, right, plus M Vm. This has to stay 0 for conservation. So from here you can find that the velocity of the boat Vm would be m over capital M Vm. Implication of the conservation of momentum. If you walk on a boat which is not being anchored or dragged, slowed down by water or any external force, if you move on the boat would move in the opposite direction, the negative sign here, okay? And its velocity would be determined by the ratio of the masses of the person and the boat. Now let's take a special case which makes it easier to understand. Let's say that your mass and it's a small boat, let's say, if they are equal, then when you move rightwards, the boat would move with equal and opposite speed. Okay? So then if m is equal to m, then v boat is equal to minus vm, v person. All right? That is why when you jump off a smaller boat, a small boat which has not been anchored properly, then what happens? Goes quickly. Similarly, when you get on, and you see this effect is more pronounced because smaller the boat, the effect is more pronounced because of this capital M in here. Okay? Now, if you go on a cruise ship, okay, and people are running around, right? People are swimming on it. Nothing is happening to the cruise ship. Why? Because mass. What is the typical mass of a cruise ship? Hundreds of thousands of tons. Typical 200,000 tons, okay? So now, if you're moving, and what is the fastest speed a person can move? 10 meters per second, right? Yeah. That you can't go faster than maybe 10, maybe 10.1, 10.01, something like that. So now, if you do this calculation, for such a case, let's use that board here. So let's say that you are, and I wish that once in your life you are on a cruise ship. So a typical person weighs 70 kilograms, right? And a typical ship weighs 200,000 tons. And what is a ton? Is 1,000 kilograms, right? And then a typical person runs at 10 meters per second. So now you can calculate, if you run as fast as you can, 10 meters per second on a ship, how much is the ship going to move backwards? How much? Probably a micrometer per second. Almost nothing. That's why when the bigger the ship, the more stable you feel. Okay? And yes, questions?
इसमें अगर बोर्ड भी साथ साथ मूव कर रही होती तो हम क्या कहेंगे कि पूरा सिस्टम साथ साथ मूव कर रहा है?
कब मूव कर रही होती?
तो इस केस में हम कहेंगे कि बोर्ड ने मोटर लगी हुई है.
ठीक है, फिर that's an external force. That's an external force. Motor, because my system is boat and person, and external force is the motor is propelling the water backwards. The reaction force of the water is an external force on the boat. So then I mean the momentum won't be conserved. So another question. When you jump off the boat, right? You're moving in the opposite direction as the boat. The boat continues its motion in water backwards, right? But why do you slow down? Why don't you keep moving? Because as soon as you land on dry earth, okay, the friction, an external force has come into play. And that stops you, and the momentum is no more constant. Similarly, the boat would continue if it was moving in a frictionless fluid forever. Okay? The only thing that is stopping it is drag force. Now this happens if you are on a spacewalk. Okay? If you're on a spacewalk with a colleague and you get an argument outside the space station, and if this colleague punches you, it's detrimental for both of you. Because you would be moving in the opposite directions with some velocity, and now there is no external force available. You don't have anything to hold on to or step your feet on something. That is why when the astronauts go on a spacewalk, they have these small micro propellers on them. That if, God forbid, if they get pulled away a little bit, they can brake. So you need propulsion for brakes as well, because there is no friction. You can slow down, come to rest, and then come back. Okay? And this is the most vivid display of conservation of momentum. Thank you very much.